Welcome, everybody, to the launch of Houdini 17.5 and PDG. My name is Chris Hebert. I'm the Director of Marketing at SideFX. We are thrilled to be back here in Montreal. Every time we're here, we really feel to the bottom of our hearts the passion and the enthusiasm of the community in the CG fields of video game development, film, TV, advertising, and motion graphics here in Montreal. And a big warm welcome to the people watching from around the world on the web. Hello. SideFX is nearly 32 years old. And the really nice thing about that is that we have a big solid foundation on which to build new features and enhancements into Houdini. And we have a deep roster of developers who love doing exactly that. So it gives me a great honor to introduce the leader of those developers, Cristin Barghiel, the VP of Product Development, and Senior Product Designer, Keating.
Hello, everyone, and welcome. This is the launch of Houdini 17.5, which is a dot release, only in name, because in reality it packs a very big punch in what it has to offer. And indeed, great to be back in Montreal after only 5 months since releasing Houdini 17. That's a very short time between two pretty big releases from SideFX, and that's not because we're speeding up development. Our pace is just as steady as ever. The reason why we're meeting sooner is to do with something completely different. And it is a new technology that we're introducing that we've been working on not just for 5 months. We've been working on it for 3 years and 5 months, almost to the dot. That technology is ready for its reveal. We're extremely proud to show it to you tonight. And we chose 17.5 as the moment to shine the spotlight on it. And that project, of course, is Project PDG. All right. This also makes 17.5 a release unlike any other from SideFX. Usually we try to aim for a nice balance between the features. Not this time. We've channeled virtually all our energies towards making this a big night for one thing only, and that's PDG. This isn't to say that we won't have a couple of really nice non-PDG features to share with you at the end of today, and Scott will do that towards the end of our presentation. But first, let's focus on PDG, which stands for Procedural Dependency Graphs. And it's all about extending the visual procedural paradigm to the big picture. All right, so before we go into exactly what it is and what it does, let me give you some background on that. So the motivation for it, it comes from two challenges that our industry, our users, are facing very frequently in your work. One of them is in VFX and film, and it has to do with ROPs. Anytime you try to do something with ROPs that goes beyond stringing together a couple of sims in a render, it quickly degenerates into an awkward scenario where you have very obtuse system of connections between the nodes, very hard to visualize, very hard to debug, very hard to extend. And that's simply because ROPs were not designed that way. And good luck trying to build a VFX pipeline on ROPs. That would be even harder. Okay? And then there's the efficiency problem. The fact that even if you're doing a sim and a render, which are very simple, very quickly you hit another roadblock with ROPs. Due to the way they cook, they make it very hard for you to get to that very important first pixel. And Scott will show you what that means in a few minutes. Now, the other inspiration comes from games. And just to pick two things, open worlds and photogrammetry. So the challenge with open world creation, procedural open worlds, is the fact that there's such a huge number of dependency to deal with. You have SOPs that help with geometric dependencies. You have Houdini engine that does a really good job dealing with the individual asset and making local changes within, the context. But there's still a missing overarching dependency system in Houdini and elsewhere as well. So if you want to build that, that's a lot of work. And then again, the efficiency question. How do you design a system? How finely grained do the dependencies have to be so that you know exactly what to update when something moves, like a road moves a bit, or a pond, or a building? Okay, something like that does not exist or does not come easily. Right now, you really have to work for it. So here's the theme, guys, right? There's something to do with dependencies and something to do with efficiencies, and that's what PDG tries to solve. So to understand how we came to the architecture for PDG, I need to do one more thing and explain to you the step we had to take mentally, the abstraction, basically, that we had to implement. And that's pretty straightforward. If you look up close, every context in Houdini, objects and ROPs and whatnot, do something pretty well, but it's very specific, right, and different than the other ones. But take just one step back, and suddenly you realize they're all about doing some tasks. So this is the abstraction. It's pretty straightforward. And you're just one abstraction away from finding that common denominator, that unifying language that lets you express everything in terms of one thing, tasks. Okay? And that extends to operations that have nothing to do with Houdini, yet operations that you encounter and you have to deal with every day in your work. So Houdini agnostic stuff. And the minute you bring those on, you're really talking about pipeline tasks. And just to play with a mental model a little bit more, imagine that we take away the Houdini component from that. Well, let's do that. Then the model still stands. And in fact, what we're dealing with is generic tasks or a generic pipeline. Okay, so let's go back now to everything displayed. And then what is PDG? Well, PDG is a system that handles all tasks and all dependencies and does so with very, very strong efficiencies built in. And since everything in Houdini is represented as a node, we went about doing that. So we introduced a new node context in Houdini called TOPs, top operators. And just to have fun, the icon that we picked for it is a top hat. That's why that's there. Okay. And what TOPs are basically wrappers around PDG. PDG is an API, and TOPs are the nodes that you're very familiar with as Houdini users. So that means that together, PDG and top nodes represent a visual task management system with finely grained dependencies and very strong efficiencies built in. And that's quite the mouthful, okay? So depending on who you are and how you relate to PDG, it could simply be ROPs on steroids. ROPs 2.0, it could be just like that. It could be your fast sim and render, or it could be your generalized task management system, or it could be the heart and soul of your whole pipeline. It's that whole gamut. And all of that is available through nodes, which means that hardly any scripting is required. That was part of the thing, not to have to be a programmer to write all of this. You'll see that in a minute. So what we're introducing tonight is this tightly coupled technology between an API, PDG API, and the node system, which is fully available to you in Houdini 17.5. That's Houdini Core and Houdini Effects. And then custom tailored for pipeline and middleware in a new product that we're launching tonight called Pilot PDG. We'll give you all the details about Pilot PDG when we release the software, but for today, we'll just focus on the technology. So let's do that. All right, so to give us an initial tour through PDG and TOPs and highlight some of its key uses in VFX, here is Scott Keating.
Thank you, Cristin. Okay, so let's dive in a little deeper so you can get maybe a slightly better understanding of why we even did this and what did we actually do. So if you think of like the most basic set of tasks that you might want to do in Houdini, or simulate something and then render the result. And this is what it would have looked like in ROPS if you wanted to do that. You would literally do this first, and then you would do this. And the problem with that is that there are actually more complex things happening here. All ROPS really did was describe when things should happen. Simulate first, and then render. But if you want to do anything more sophisticated with this, you need to start thinking about things inside of these jobs. You can't think of them as these huge, coarse objects. You need to think about what each one of them actually does. And so if we just zoom in a little bit, you can start thinking about the things inside of these jobs as the frames, right? There are a certain number of frames for a simulation. There are a certain number of frames for a render. So that's great. We're thinking about frames now. We're thinking about these smaller units instead of these large picture things. And if we look a little bit closer and start thinking about how you actually work with frames, well, if you're working with a simulation and you have a bunch of frames like this in a row, and then a render job, there's not really any connection between frames generically, right? A frame is just a thing that you're going to use for some result. It's a slice of time. Well, a simulation actually has sort of an implied dependency, which is to say that frame 1 comes first, and then frame 2 needs frame 1 to exist before frame 2 can start. It's a natural dependency that a simulation requires the previous results to continue. But if you look at a render in isolation, a render can happen in any order. Once you have all the stuff that you need to render, it can happen in any order. It doesn't matter. But when you have two things together, like a simulation followed by a render, there is another implicit dependency here. And that dependency is that frame 1 of the render relies on frame 1 of the simulation, right? So simulations rely on the previous frames, but renders rely on any frame of the simulation being complete. And as soon as we started thinking about this idea of like, well, what we're really describing here, instead of frames, is really dependencies. That's what we're describing. We're not describing what the work is. We're describing the way those things rely on each other. So let's jump into Houdini and take a look at how this actually would work. So I'm just going to run this pyrosim just so you can kind of see how quickly it renders in Houdini generically. And then we're going to put down a top network, which is this new node context. We're going to drop that in the network. We're going to dive inside of it. There's the little top hat icon. And inside here, we're going to put down a node that you're pretty much already familiar with, the ROP geometry node. And this is literally, you point it at the geometry you want to write the disk. In this case, a simulation. We're going to render out 100 frames of this simulation. And we can use this new task graph to do it. So right away, you see a huge difference in the UI. Immediately, you see the number of tasks in this operator. If you look at the numbers on the left, you can see how many are going to be cooked. The bright green ones are the currently cooking ones, and the darker green are the finished tasks. And you can see we're cooking along here. We get a nice live preview. We get a nice little spinner telling you what's working. But you can see that it's kind of like weirdly slow, right? You just saw how fast we cooked that other simulation. Why is it so slow? Well, let's turn on the performance graph. And you can see that further and further down in this graph, we get these darker red nodes. And that means it's getting slower and slower over time. And that's sort of odd. Why is that happening? Well, essentially the reason that's happening is that we haven't told it there's a dependency between these frames. So we can turn on all frames in one batch. And we're just going to re-cook this graph now. And you'll see that we get speeds approximating what we did in the viewport. Except you'll notice that the timeline is not playing back while I'm doing this, right? So we're not forcing this session to cook that stuff, which is what would have happened in ROPS. Instead, we're doing this in the background. Right, so you can be working in a session of Houdini and in the background be generating results to disk. So here we are. We've got a nice complete simulation. So the next task we want to do is render. So let's go ahead and add a render node to this. So we can literally put down a mantra top, and that just points to a mantra node. And we're going to just generate the node. And that means just see how many tasks this is going to do. And we already know there's 100. You can also see that I can middle mouse button and get some PDG specific information here. And everywhere I click, we draw a line of dependency to the previous work. So as you would normally, I'm just going to put down a file SOP and I'm going to point it to a file, but I'm actually pointing to something called PDG input. And what that is the result of the simulation. And now I can click around and preview it in the viewport. What frame is going to be rendered at what time? And then I'll cook this node. And so as I'm cooking it, you'll see the render is going. But something interesting is that if you look at the top, there's a little green check mark under ROP geometry. And that means we're not recooking that. And again, in the ROPS workflow, you would have recooked those results before you started your simulation. But TOPS is intelligent enough to check on disk to see, like, well, did these results already exist? And if they do, I'm not going to do the work again unless you ask me to do it. And so you get this nice way of working. If you're just prototyping a setup, you're reducing the amount of work you have to do with each step. But let's clean up those files on disk. And we can actually do that through a menu because each top knows the geometry it created, and rerun it again. And you'll see now from scratch, as soon as a work item is ready in the ROP geometry, we can preview it directly from the middle mouse button information. And also, as soon as a frame is ready to be rendered, it starts rendering. It doesn't wait for the whole simulation to be finished. And then we can pop open a frame and preview it directly inside of Houdini without leaving the context that you're working in. And so again, this is really a workflow booster for a workflow that already mostly existed in Houdini, but now much more efficient use of your time and your render resources, and much easier from a setup point of view because you can directly see the results in the network itself, even if you're working locally or on a network. So typically in a pipeline like this, the next step would actually be to create like a little preview video of your render. And we have a bunch of utility nodes in TOPS that let you do that. This is a FFmpeg encoder. But you can see that we're drawing a whole bunch of work items in here, 100 of them. And what that means is that we're going to generate 100 videos, one for each frame. And we don't actually want that in this case. Some cases you might actually want that, but probably not. And so what we need to do now is start thinking beyond the concept of a frame. Because a frame is not enough information as soon as you get outside of things that are time dependent, right? And this node that I just placed down called wait for all, this is a special new node in TOPS. We call them partitioners, but it essentially is a way of describing a dependency. So it's a new type of thing. Instead of working on geometry the way SOPs would work on, this works on a dependency. And there's a bunch of those in TOPS, and we definitely don't have time to cover them all, but there are things like, let's partition things by an attribute, or even spatially, across space, break things up spatially and bring them together. But in this case, the wait for all does something very simple. It literally says, wait for all of the incoming work to be finished before you send work downstream. And so if you see as we cook this network again from scratch, there's a little spinner and one partition, which is this little rectangular block, waiting. And it's waiting for all the work to be done above. As soon as it is, you get a nice little check mark. We get an FFmpeg encoded video, and we can immediately look at it. So again, you're taking these very common tasks that you normally would do in these kinds of scenarios, and we're allowing you construct them with networks. So again, all stock nodes, no coding to do this, no scripting. It's all built in. So let's move on now to something slightly more complicated. So another thing people did with ROPS that was really useful is this idea of creating a wedge. And a wedge was essentially a way of doing variations on something. So you would set up some parameters and say, well, I want 5 random values for this parameter, and I'm going to override some other parameter to do it. And that was possible in ROPS. But in TOPS, it's a much more fluid way of working. So here we've got this very simple asset. It's just a SOP asset. It builds a brick wall. It has a couple of parameters. And we want to create variations of this geometry. So we're going to put down a wedge top. We're going to say we want 5 variations, so we're going to change the wedge count to 5. And I can immediately cook this node now and see the jobs, even though it's not even doing anything yet. It's just generating that work ahead of time. Then I can say, OK, I want to create 2 variables. So the first one is going to be height, and I'm going to create a range of values from 2 to 10. So we're going to get 5 values between 2 and 10. Then we can go ahead and target a parameter on that node. And we can do that just using this little convenient drop down here, this chooser that lets you pick a parameter. And then you can see that I can click on a work item and see that height has been added as an attribute on this work item. So you can embed data on a work item to be interrogated by TOPS later. And as I click these work items, you see the wedge variable being evaluated in SOPs. So I can go ahead and add a width, and I'll just set a different range here and copy our other path up. So what I'm doing here is just setting up values that I want to use in my range. I want to create essentially 5 different walls, each wall a different height and width. So you can see now as I go through the work items by clicking on them, I get an update in my viewport of exactly what I'm going to get. So again, you're not working blind, which is what used to happen in the old workflow. You would set a range of values, you would render it, and come back and then see the results. Now the next thing you want to do is actually make more variations based on this. And that was something that it was technically possible in ROPS previously, but very difficult to set up. But because we have these very clear dependencies in TOPs, we can just go ahead and add another wedge node after the first one. And I'm going to go ahead and set the wedge count to 10. So for every incoming work item, we're going to create 10 more. And again, I'm going to use, this case, the number of bricks, set a range of values. And I'm going to just cook this to generate the items. And you can see now I can click on each work item above and see that, well, I'm actually generating 10 tasks for every one above. Then in SOPs, I'm going to do something different here, just to give you an example. I can use @numBricks, which is the variable we created, and PDG will change that value at runtime into whatever you've set. So you can see now I can click on the work items, and that variable is being evaluated by TOPs to give us different walls with different numbers of bricks. So we've taken a pretty mundane task, and we've more or less automated it here. But let's take this a step further and say, like, okay, well now I want to render each one of these, right? So just essentially redoing the step that we did earlier. So we're going to go ahead and vary the geometry, and that's what this first block of nodes is doing, the ones that I just set up. And then in the bottom right, we're going to render each one of those wedges, each one of those variations. Then we're going to wait for all the frames to be rendered. And then we're going to use another sort of utility node, which actually uses image magic, to create a contact sheet of all of these images. So again, we're taking very common pipeline-y tasks that artists go through every single day, and automate them. We're going to create that montage. And this is the result. So we created all the wedges, and then we built this image. This isn't just for this slide. This is the actual image that's rendered out at the end of this network. So this is great. So now you can actually not only generate all this stuff, but compare it in context, possibly even in the scene that you're rendering it for, but in this case on a very simple setup here. And you can see 5 versions of the green wall, 5 versions of the orange, the blue, and so on. Now we'll take this another step forward and make a unique simulation for each one of those. So here we are, we're just in Houdini. We've basically set up a standard sort of rigid body simulation. None of this is top specific. In fact, all of this was just set up using the rigid body shelf tool. The only main difference here is that the geometry that's being read in, the wall, is coming again from the PDG node. So we're channel referencing a value generated by those wedges so that we can get the right geometry at the right time. And then we just have a standard simulation. So there's nothing in here that's top specific. We're just going to do this basic simulation, but we want to do it for every one of our walls. So here we are. We've set up a ROP geometry just like we did in the first example. And if we go ahead and cook that now, you can see, again, simulations being generated very rapidly. These can be run in parallel, right? So they can be split into separate tasks in the background, run in parallel. So you're not waiting for one simulation to finish and then getting the next one. You're doing them all simultaneously. So as Cristin mentioned, the time to first pixel is decreased as much as possible. And so now let's go ahead and do that. We're going to hook up exactly the same network we created before, except for rendering these simulations out. So again, you can see multiple frames being rendered at once, and that's because there's no dependency between those. Again, in parallel, we're grabbing available work items and we're rendering them to disk, and you can see them showing up over here on the side. And then we're using some of these dependency nodes that I described, these partitioners, to say, okay, once we have all of the frames, let's gather all the matching frames together. So every frame 1 of a simulation, let's get all of those. Every frame 2 of a render, let's get all of those. And put them all together to make a sequence of these montages. And so the result is something like this. So not just a static image that shows you all of the results, but all of the frames all together. Again, because we can describe more complicated dependencies. We can say, I want all of the frames in order, one at a time, put into a sequence, and then render the entire sequence. And the reason this is important, apart from just the fact that it's kind of neat looking, is is when you're actually trying to evaluate this. When you're doing this kind of wedging, the goal is you want to find the sim that's the best, the one that you like the best. And in order to do that, you really want to see them in context like this. You want to be able to compare them directly. So if you're sitting with a director or a supervisor, having something like this is an excellent way to really get to the result as quickly as possible. Now let's go ahead and add a smoke wedge into this example as well. So here now we're rendering everything at once. And if you look in each sort of column, you can see as soon as a wedge is ready, we begin rendering a rigid body sim, and as soon as enough of that rigid body simulation is finished, we start rendering a smoke wedge. And so what that means is all of them are happening at the same time. As much of your compute power is being used simultaneously as is possible. As soon as one rigid body sim is ready, a smoke simulation starts, and so you're maximizing your compute power. And then, as I said before, we're going all the way down to creating a montage. So the result of this is a static image, a rigid body sequence, and a smoke simulation, all rendered to disk. And the final result is this, as we said before. So again, a really powerful way of setting up these dependencies that was very difficult to do previously, and really frees you up to worry about setting up the simulations and letting all that other stuff just happen more or less automatically for you once you set up these graphs. And of course, they can be applied to anything. It doesn't have to be wedging. It can be any model variation that you're feeding into the system. And again, this is really important from an artist's perspective. It's not just about producing as much stuff as possible. It's actually useful purely from the perspective of, like, I'm dealing with a client. The client has said to me, I need a motion graphics video, and I need something that looks a little bit like a seashell and a little bit like a sail. Can you please show me a bunch of variations of that? And that happens all the time. And so, yes, you can do that, and it would be great to give him not just 5 variations, but say, look, here are thousands of variations of this thing. Here they all are together so that you can test which one is the one that you want to use, and you don't have to wait, potentially tens of thousands of these. And the awesome thing about this particular example is that it's not just an example. Intagma, who are awesome, are doing a bunch of tutorials to explain exactly how this was done, and it will release very quickly after the release of Houdini 17.5. So you'll be able to jump in and start learning how this stuff really works as quickly as possible. But it's not just about variations that you want to compare to each other. Sometimes you literally want multiple versions of a thing. And so here's an example, a little more of a complicated example, producing a more complex asset than the rigid body simulation, where we want to create different versions of these Jersey barriers. And we want to add different texture maps. And not only that, we want to take that high-res model, we want to bake it out into a bunch of texture maps, then we want to apply those materials back on. So here's just an example of the wedging. We're not going to have to go through this every time. I think you're getting it by now. But you can see that we can click through the variations. We can see, in this case, 3 connected wedges. So wedges of wedges, variations on variations. And again, some nice information in the middle mouse button menu there to tell you, like, which wedge number this is, how many of this exist, what are the parameters I'm overriding. But the interesting thing about this setup is that it goes outside of SOPs and into COPs. And so you can see we're baking mantra textures. So we're actually taking the high-res geometry, automatically generating some low-res geometry for it. We're baking each one together, outputting the maps, doing some extra compositing on them, and then outputting the result as a final render with the new materials applied. So again, this isn't just about saying, oh, I want 5 versions of something. It's about being able to tie all the tasks that you need to do with this thing together in this holistic place where you can say, render something, give me the result, send it to compositing, add the texture maps, apply a material to it, and then render. And again, the result all together like this to show you the different variations that are possible in this particular setup. And so here's another example of that exact same setup, except taking advantage of something else that's really interesting about the technology here, the PDG side. And that's that the API is very simple. In not a lot of work, you can generate your own nodes that operate on things outside of Houdini. So in this case, this is the same setup that we just showed you baking with Mantra, except now we're baking with Substance. And not only are we baking with Substance, a final montage is using Photoshop. And so these two nodes were generated by these third-party guys pretty quickly as sort of prototypes to see, like, well, can we plug into this system? Is it useful for us? And they were able to do that without a lot of effort in really just a couple of days in order to plug into something that has nothing to do with Houdini. This is completely outside of Houdini. And of course, you get a result as you would expect with some nice little information applied to it, like which version of this embedded in the file name. So again, really freeing you up to connect parts of your pipeline that have nothing to do with Houdini necessarily, but all controlled by this one mechanism. So far, that's been all about, like, okay, I want to generate a whole bunch of stuff, like tons of stuff, and I want to dump it onto disk somewhere. And that's great, and that's really useful. But there's sort of the other side, which is that, well, I need that stuff now. I want to do something with it, right? And you want to be able to do that as an artist. You don't want to just like, oh, just take everything and load it into Houdini. So let's look at how you can use SOPs integrated with TOPs directly. So first of all, we've got this little tool here, and it just generates a bunch of plants. So we just click through these work items, you can see we've got all these plants. And we want to use these as a library for essentially a layout tool. So I'm just going to create that asset library, and that really just means write those things out to disk. And here we are now in a top network that does something really interesting. It looks at a folder on disk, and it can use wildcards to say, give me everything in that folder. And not only that, give me information about it, like what's the file name? And I can then use that in SOPs as a tool that goes into that library, grabs any item that's in there, and randomly picks the results. And then I can just add more of these and update the library automatically. So it goes onto disk, it says, oh, there's more files here, I'll get you those as well. And now you can work as SOPs pulling information from TOPs. So again, an interactive workflow. Now the issue here is that these models are actually quite high res. We hit a 20 million polygon limit pretty quickly. And what happens is when we cross that threshold, we start adding these bounding boxes as sort of placeholders. And that's just how the viewport works in Houdini 17.5 and 17, in fact. And that's usually actually what you want. You want to keep your viewport nice and interactive. You want to cull geometry if you need to. However, if you're in a layout circumstances and you really want to get a feeling for, like, well, what plant is that? Like, I can't tell by looking at that bounding box which plant it is. So let's see how we can use, again, a hybrid workflow to make this a bit easier. So here we have that same wedging setup, except now we've embedded a SOP network in the middle of it. And this SOP network takes advantage of compiled SOPs to do a very simple operation. It takes this high-res plant at the top, and it creates this extremely low-res version at the bottom, and then we just add that into our asset library. And now in SOPs, I can say, which file name is this? If I'm rendering the proxies, get me the one that's .proxy. And now I can be an artist, and I can take my tool, and you see, it stays very interactive. I can paint more and more and more of these, and because they've been poly-reduced so much, I get a good idea of where these plants are going, and if I want to, I can now switch to the high-res one. Because PDG has managed, like, which file name have I got, which one are you asking for, and it can hand off the correct information as you do it. So it's very easy to say, show me the high res, because I want to make sure the lighting looks right, but while I'm working, show me the low res. And again, this is a truly hybrid approach, TOPs existing inside of SOPs as an artist tool. But let's take like a step back and think of like the whole pipeline. So here we have Crag. Normally when we do these videos with Crag, he's like being pummeled by things or he's smashing something. Here we said, you know what, it's just a peaceful, quiet walk in the forest. That's it. It's like this is his off time. So if you actually were generating a scene like this, let's say this is a shot in your film about Crag, and this is something that needs to get done. So depending on who you are in the pipeline, if you think about a shot like this, you actually think about completely different things. If you're a different person, you have a different perspective on this shot. So for instance, if you are an animator, when you look at this shot, you probably see something like this. You see a rig. Maybe it has textures, maybe it doesn't. And that's what you're dealing with. And maybe the background, because you want to get a feel for where he's walking around, but you don't need the trees, you don't need the lights, you don't need any of that information. You're truly just working with the rig. So from this perspective, Crag is not really a character at all. He's a rig. If you're an effects artist, you don't probably care about the lights. You may not care about the texture maps. You don't care about the rig. You want a geometry cache. You just want the output from the animator. And you're going to add effects onto here. Maybe you're going to add dust when he hits the ground. Maybe you're going to add fireflies in the air. Whatever it is, you only want some specific pieces of information. And from your world, from your point of view, this is the only thing that matters. And finally, maybe you're doing look development. Maybe you're a lighter. You want to pull in as much of the detail as possible. So you want to pull in the texture maps, the full background, the full character as a geometry cache. You want to get all that in so you can do your job in the most efficient way. And there's a lot of ways to approach this from a pipeline standpoint, because you can say like, well, I'm an animator, I'm going to save a HIP file with my rig, and then if you need to see it, well, I can give you my HIP file, and you can make sure you have the asset, and you can load it and look at it. Or if I'm an effects artist, I can localize some of these files and try to embed them, but it becomes complicated. You're working with files that really you shouldn't be touching. If somebody else has a file that's in progress, you definitely should not be modifying it in any way. And so really what you want to do in a scene like this is you want to think about this as not HIP files. You don't want to think about it as like, well, I need the thing that built this. Instead, you want to think about it higher level. I need Crag, and I'm an animator, so I need his rig. So PDG can actually be used to do that. You can think of it as a purely pipeline tool, something that happens to use Houdini in this case, but is really about grabbing the correct piece of information. So imagine that at the very top of this network, we need to ingest some sort of a shot description, whatever that happens to be. It could be, maybe it's just a CSV file with a description of the assets for each shot. Maybe it's just folder structure somewhere on a network that says like, well, shot 1 is in this folder and the assets that are required are in nested folders. Or perhaps you're going to shotgun. And all of the things that I just described are possible with PDG, including the shotgun integration. So you can directly connect to shotgun and grab this information. And once we get that, once we know what's in a shot, we just need to start saying like, okay, let's do some work. And so PDG isn't just about pushing things blindly through a pipeline. It can interrogate some of the information. It can say, what is the file name? What's the asset type? If it's a database, if you've applied some metadata to that, let's pair that up so that we know what we're actually dealing with. And the reason this network is sort of large is not because it's actually very complicated, but just because we keep splitting the data up more and more to get more specific information from each asset. And once we've done that, we can do something really interesting. We can build a HIP file. So no HIP file exists with these items in it. And we can do that using something called a Houdini command chain. And there are generic versions of this as well, but we're focusing on the Houdini ones. And what this allows you to do is send commands to a Houdini session using HOM. And so PDG can say, okay, you've given me a whole list of assets. I want to instantiate those assets in a HIP file and then save it on disk in a local folder so you can have access to it. And it literally just does that with some very basic HOM code here, some Python code. And you can see if you glance at it that it's really just like, am I in HDA? Well, then install an HDA. Am I keyframes? Then apply those keyframes to the rig, and so on. But obviously, you don't want to deal with that huge network, mostly because it's not necessary to interact with it. Once you've built it, once somebody has constructed it, you can create an asset out of it. And if you're used to Houdini, the idea of making an asset is not like a surprise. Like, of course you can make an asset out of it. Where this becomes really interesting is that, first of all, you can just drop this asset into a HIP file and start running it, which is great. But the other thing is that it means that parts of your pipeline now can be assetized. They can be turned into a modular thing that can be connected with other parts of your pipeline. And not only can they be connected together like that, because they exist as assets, they can be updated. They can be replaced with other assets. They can be checked into some sort of asset management system. So suddenly your pipeline is not this static, rigid thing, which is like 4,000, 5,000 lines of Python code. Instead, it's something where it's like, oh, I just need this one piece. I need the HIP file builder part. I'll just put that in my scene. And so you can tie these things together and get really good interactive pipeline actions. So here's just an example of saying, okay, I want shot 1, I want the cameras, the lights, and I want the geometry. And then when I cook this, and these nodes are inside that asset, by the way, we're going to generate this lookdev.hip. You can see that essentially what's happening here is that we're looping over everything that we've requested, lights, cameras, and so on, and then we're sending a command to Houdini to say, load that piece of data. And then you can see in the middle mouse button information here, that's output as a HIP file. So you can directly access it here, and the result looks like this. We've pulled in the shot the camera asset, the lights, the set, and you can immediately look through the camera and start seeing what the scene actually looks like. And again, this is on demand. This HIP file does not exist until you need it. And so now things in your scene or things in your shot are no longer rigid. You can just say, I need these things, please give them to me. I need these things, please give them to me. So on that note, let's say you're an animator, and maybe you need to make some modifications to something that exists. Maybe you're starting a second shot and you want to start from something that already exists. So in this example, we've split the rig and the keyframes into separate files. So they exist separately from each other. So the rig no longer has animation. Animation is its own asset by itself. So now I can say, okay, I've asked for the rig, I've asked for animation. There's no camera, but you can see here's Crag, here's his rig. I can play the animation because we've applied the animation to that rig. But this is a live rig. I can actually go in and start editing keyframes now. And because the keyframes are separate, they don't live on the rig, they live individually, it's perfectly safe for me to do this, which is what you want. If you want to just see a rig, it should never be dangerous to do that. You should be able to say, please give me the rig, give me the keyframes, I'm going to make some edits. Especially if you imagine like layout tasks earlier in the pipeline where maybe you do have a rig and you're doing some basic setup, you're doing look development. Very, very important. Okay, so we've got all these pipeline tools. It all works together. That's awesome. But so far, everything has been basically this idea that I have like all this work, some amount of work. And I just want to break it up into a known number of things, like there are 100 frames, or I want a rig, so that's one thing. And that's mostly what you want. You want to know how much work you're going to do. But there are concepts that are possible in PDG that were absolutely impossible to do previously in Houdini. So let's look at a scene like this. Okay, we've got a bunch of crowd agents. They run through this field. Every time they hit one of these sort of jelly beans, they explode and go flying. That's great. So in a typical workflow, even with PDG, if we use the exact same setups that we've described so far, what would happen is we would basically say, okay, first of all, I need to find out where these things are going to happen, right? And so as soon as you think, well, I need to find that out, if you look at multiple simulations, and this isn't even a wedging example, imagine that you don't know what you want yet. And so every time you run a crowd sim and you change the number of landmines or the number of agents, there's no way to know what the outcome is until you run that simulation, right? There's absolutely no way to do it. You can't do it in advance. And so if you think of what we've described so far as like a static network, then we would have to do something like this. We would have to say like, well, let's run the full simulation first, just like we did with our rigid body simulations in the first example. And once we've run that whole simulation, now we know we have a static number of things, run those pyro sims in parallel, right? So essentially, we're just accumulating the points. We're saying that one was triggered, this one was triggered, that one was triggered, and when we're done, let's just run all of those simulations at once because they don't really need to talk to each other. And that's great. That's actually a very useful thing, and in fact is a very optimal way of running this. But sort of as a thought experiment, like what if we could start simulating a pyro sim as soon as an agent touches one of those objects? And instead, what you would get is something like this. As the simulation plays, you immediately start rendering pyro simulations as soon as you know one of those things exists. And this is something called a dynamic network in PDG. This means that we don't know in advance how many work items to do. Tasks are generating new tasks as they come across them. And that means you can say, every time an agent touches one of those things, please start generating a pyro sim with these settings at this point in space. And this is essentially what that network looks like. This is literally the entire network. So first of all, we have our crowd, and it's playing, and you see as these little dots start filling up, once we get to around frame 12, we find mine hits. And you can see we've got 3, 5, they're filling up in the middle. But as soon as we have a mine hit, we start rendering a simulation on the far right. And so now we're getting as fast as possible results. There's no way to do this any faster. As soon as a sim is available, you start rendering it. And it does this based purely on what the crowd sim is doing. And then at the bottom, we have another one of these gather dependencies where we're saying, like, well, we have to be sure that all of the sims for that frame are ready before we start rendering. And so it waits, it gathers them as they come in, and it can start rendering as soon as possible. So you will have noticed that it starts rendering the final frames even while the simulations are still running, because it can guarantee that, well, there are no more frames rendering before this, so it's safe to render them. And so suddenly you have this really powerful way of working where if your goal is that you need a result as fast as possible, like that's what your goal is, these dynamic networks allow you to do it. Now, having said all that, the reality is in most film VFX productions, television productions, these simulations could literally be a day long, right? They're not a short amount of time. They could be days long, depending on the type of simulation. So in most cases, you actually don't want this dynamic network because you don't know how many jobs are going to be created. Imagine you set up a crowd sim and then you clicked, simulate, and you left and went home, and you generated 7,000 high-res pyro simulations, right? Which would be possible in this case. So in most cases, that's not what you want. You want statically known. You want to be able to say, you know what? I need to know that there are 300 jobs that will happen when I'm done. And all the stuff we talked about before this would let you do that, which is awesome. But if you start to imagine other scenarios, not being driven by a simulation, but being driven by a human, like there's a person interacting with this, something where I want to minimize how much I need to do in order to get a result because someone is going to change the inputs, and I don't know how they're going to change it. And that has some application in film and TV and effects, but where it's really important is in a games workflow, where an artist is sitting, building a level in a level editor, and they make a change, and you want to do as little computation as possible to get a result, right? And being able to track these dynamic dependencies is what would allow you to do that. So to help give you some better examples of that, I'm going to welcome Cristin back to the stage in order to introduce our game section.
Thank you very much, Scott. The next chapter belongs to Ken. I want to say a few words about Ken before he takes the stage. Ken is a senior software architect at SideFX. He's also the creator, lead architect, and lead developer of PDG. Pretty much, PDG is his baby. Ken has been holding his breath, in his own words, for over 3 years now. So hopefully he'll get to excel at the end of the day today. He's iterated the architecture many, many times to make sure that it's strong enough, stable enough, scalable enough, flexible enough, and also user-friendly enough that we can put it for you to use starting today. And he was able to achieve this with the help of an amazing team of developers who've been working tirelessly ever since we started until today. Today is their day, so please join me in giving Ken and his team a big hand.
Thank you, Cristin, for the very flattering introduction. I just want to take a moment here to give a quick shout out to the team in Toronto, to Taylor, who's in the audience with us, and to Chris G, if you're out there watching. We've all worked extremely hard to get to this point, and I'm just so proud to be up here representing all of us and our collective work. Okay, so back to the presentation. I'm here to tell you a little bit about PDG's fit with Houdini Engine and game development. You've seen already how PDG fits into effects workflows and film. Now, Houdini Engine is probably something that doesn't require any introduction today. It's been out there for a couple of years now and making a pretty big impact in both games and film. It's capable of a great many things, but among the things that Houdini Engine is capable of is generating big-scale procedural environments like this. Okay? So here, this is an environment that's completely generated procedurally. And we see many elements in here. We see, terrain, we see vegetation, there's a little tower perched up there, the road. In the distance, we see an airport, and even, things like bridges and tunnels and so forth, okay? So Houdini Engine is certainly capable of generating all of these things, and that's great, but today it still has one significant drawback, and that is that it considers all these elements as individual assets and that are totally independent. So by that I mean if you want a different terrain tile, you go select it, and the interface pops up. You wiggle the sliders, and you get a different terrain. If you want a different version of that road, you grab the road curve, you move it, and you get a different road. Okay, that's all well and great. It's way better than modeling this stuff manually. But in reality, it's still not capturing the fact that these things really have a relationship with each other. By that I mean, if I move the road and the road is now kind of cutting into the terrain, shouldn't the terrain be deformed, right? In response. And if I move that road and it's now kind of floating in the air, maybe we should put in, this bridge support here, right? And for vegetation and stuff like that, I shouldn't be scattering that stuff onto the terrain until after the deformation is complete. Okay? So today, these dependencies aren't really captured by Houdini Engine itself. To capture these dependencies, you'd really need to create this custom system to do that, and that comes at great time and expense. Or, if you don't have the budget and time to do that, you just end up not doing it at all. And in which case, you're left with a really messy workflow problem where you have a couple hundreds of these things scattered in your level, and you have to go and pick out each one of those things and work on them one by one. And that is, really not efficient from a workflow standpoint, nor a computation standpoint, and it's just really, really error-prone. Okay? So with the advent of PDG, what we can now do is really create, for the first time, visual procedural systems that can really take all these elements together and consider them holistically together and capture their relationships. And we can do it, of course, with, as you might guess, a PDG graph. So here is one that is really going to describe the relationship between all these elements, the terrain and roads and bridges and tunnels and rocks and plants, and how these things all interrelate to each other. And we don't have time right now to get into the specifics of the details of this, but don't worry about it, because Kenny Lammers and from Indie Pixel is going to be creating a full-fledged set of tutorials showing you step-by-step how we put something like this together. And I'll quickly mention that all of the nodes here are just stock nodes. So everything you're about to see in the next slide, you can achieve this completely without having to write any code at all. Okay, so let's take a look at what this actually looks like once we have built these relationships. So here I'm going to just kind of grab this road here, I'm going to move it up, and right away you're going to notice that only the two terrain tiles where that move actually happened was actually impacted. The rest of the environment wasn't touched at all. Notice also the sequencing. The road was computed first, followed by the terrain tile, followed by the scattering, right? And notice also there's a bridge there now where there was none before. So we got the automation, we got the right sequencing, and also we're getting the scale here, right? So these two terrain tiles are actually being computed at the same time in parallel. So we're getting that parallelism as well. We are not doing other stuff just for clarity here so you can see what's happening. But in fact, while this is happening, I can go grab another piece of road, I can do all kinds of other stuff, and work completely asynchronously, and the system will just kind of just keep on delivering. And then one last point, you might notice that that bridge there that just popped up, to Scott's earlier point about dynamic versus static, here is a very dynamic situation. When we first looked at this thing here, there was no bridge. And when the curve was moved, all of a sudden there was one. So whether there's a bridge or not really depends on whether what the user actually did, right? And we can't know that until he's actually finished placing the road. Okay. So the other really nice thing about this is that everything you're seeing here it just happens to use Houdini Engine stuff. It's not limited to Houdini Engine. So in that graph previously, I could have just putting any kind of custom nodes in there, and it would just work just the same. Okay? So anything that involves asynchronous compute, anything that involves automation and scaling, you can basically achieve it with the same in the same way, basically with PDG and the Houdini Engine API. Okay, so that bit is about Houdini Engine and the fit of PDG to games. I have one more important thing to talk to you about, and that is machine learning. So machine learning is just one of these hot button topics. It's already having a significant impact in both games and film. And it turns out that PDG has a really nice fit with this important upcoming field. And this is because machine learning requires just a ton of data. It needs a lot of processing as well to crunch through all that data as it's doing its training thing. And finally, it needs a lot of trial and error to kind of get it right. And these are all things that PDG just happens to be really, really good at. Let's take a look at how PDG can be applied to machine learning. And we're going to show you this through a couple of examples. But keep in mind that these things are just examples around terrain, okay? They're here so that we can clearly understand the relationship between PDG and machine learning and see it in context, but they're not themselves yet ready for production, okay? So with that in mind, let's take a look at the first example, and this one is around fast terrain erosion, okay? So the idea here is that, we're just gonna take a piece of terrain and we're gonna erode it, right? And we have lots of tools in Houdini to be able to do that. This all works great, except the fact that it just takes a long time to do. And so the idea here is, can we create a machine learning system that, it's going to give us, pretty similar results, but and hopefully just do it a lot faster. Okay? So for those of us in the audience who are not familiar with the process of machine learning, I'm just going to quickly lay out the steps for you. So in general, machine learning, really, you can't learn anything unless you give it lots and lots of examples, right? So the first thing we're going to do is just basically create lots and lots of data, examples of uneroded terrain versus eroded terrain, and kind of show it to the system, and hopefully it learns that. For each of these pairs that we create, we're going to want to flatten it to a pair of images. And this is because our machine learning algorithm happens to be image-based. Okay? On the left, you see the original uneroded height map. And on the right, you see a color image, because after erosion, we actually get a couple more channels. We get the debris and the water fields. And we're using the green and blue channels for those. And that's why that's a color image there. So once the data is ready, what we want to do is we want to create an appropriate machine learning model. And by that, I mean something that's, it's got the right configuration to be really able to capture the information we're showing it, right? And with the model created, we'll run the machine learning training. By that, I mean show this model all the data that we've gathered, so it can learn. And at the end of that, we'll take a look at how the model is doing. Hopefully, it's doing well, but if it's not doing well, then we're going to go back up and we're going to just tweak the model and just keep on doing this over and over again until we get something that is producing good results. And hopefully, at that point, if we show it something it hasn't seen before, it'll make a really good guess and give us good results. Okay. So with that in mind, let's take a look at what this looks like with PDG. So just like Scott has shown you before, PDG is just capable of crunching out tons and tons of variations, but that doesn't really stop with just effects. So here we're going to create lots of different variations of the terrain, different roughness, different offsets, etc., and create all these versions of the terrain that we're going to erode to create pairs like this. So on the left is the uneroded version, and the right is the eroded version. And once again, you see in the coloration because we're using the blue and green channels to represent the debris and water. So next, we're going to go and, like we described, we're going to flatten this. Okay, so on the left, you've got the uneroded height map, which is black and white. On the right, the eroded version with the water and debris. And we're going to montage this together to form these image pairs. And we're going to get lots and lots of those, like so. So at this point, our data set is ready, okay, for machine learning. And now we need to kind of figure out the right model to machine learn with, right? Generally, these days, we have a pretty good intuition on what kind of model to use, but there's no really hard guidelines. And there's just so many different ways you can configure these things, like how many layers do I use, how many, if I'm doing convolution, what's the filter size, what's the learning rate. So these different configurations in machine learning speak is called hyperparameters. And so because we don't really know what's going to work well, people just end up trying lots of different stuff at the same time. Well, they tried in serial, but now that we have PDG, we can really, instead of doing it one at a time, we can just say, hey, you know what? Let's try all of these things together at the same time. So what we're really doing here is hyperparameter space searching with PDG. Okay? So I'm going to wedge out a couple of different variations here. On top, you see I'm trying 2 different settings on the number of layers. And the third node down, I'm trying different filter sizes and 3 different variations of that. So 2 times 3 is 6 total different variations we're going to try. And then we're going to create the machine learning model and run that machine learning. So this is the only step that actually really requires any kind of machine learning expertise. You need somebody who knows the machine learning stuff to kind of alter the training code a little bit based on the upstream wedge settings, right? But once we do that, we can run all 6 of these things in parallel. And this last step here, we're going to analyze all the results and produce ourselves a little report. OK, so once we have done this, we can take a look at the report. And it looks something like this. You can see the upper left hand here is clearly something that's not doing so well. You can even sense it by the way the kind of lines are just jumping all over the place. And you can intuitively see that on the bottom right-hand corner are things that are just converging a lot better. And indeed, once we take a look at the final results here, and we really see that. The one on the top upper left hand has just got pock marks all over the place, and it's just a mess. Whereas on the bottom right-hand corner, things are looking a lot better. Okay? So once we have this, we're going to kind of just pick out the best one of these, and then and show it something it hasn't seen before. So one of these images here is produced by machine learning. Can you tell which? Turns out the top one is the one created with SOPs, with actual simulation, while the bottom one is the one that machine learning produced. It hasn't. The amazing thing is that it hasn't really seen this at all. It's just a totally new sample, and it just guessed at the result, and you got that. So it looks very, very similar, but the only thing is it's like 50,000 times faster. So it's pretty crazy. And what's also really cool about it is that you can see that it also learned the debris and water fields as well. So you can use this as like a preview. You can use it as a first starting point and just kind of carry on the work from there. So yeah, so crazy speed from machine learning. But you might argue that sometimes the speed doesn't matter because what's the difference between something that's producing a result for you in 1 second versus something that's producing a result for you in 0.1 second. So that you might be right about that, but unless of course that extra speed, that blinding speed, is giving us different ways of creating stuff, different ways of interacting, and then that really becomes really exciting, right? So that's what we're going to show you in the second demo here. We are going to show you how we can take ordinary sketches and turn it into realistic-looking terrain. Okay? So in order for machine learning to produce realistic-looking terrain, we need to show it realistic-looking data, right? There's no magic here. So what better place to get realistic-looking terrains than the USGS? They have basically, the satellite scans of effectively the entire planet. And us being Canadians, we're partial, so we thought, hey, why don't we just take a chunk of the Rockies and train it on that and see if we can, produce something sensible here. Okay, so that's what we're going to show you next. So the process here, just like before, we've got to get the first step, as always, is just getting our hands on the data. And in this case, we're going to download it from a website, the USGS website. Then we're going to generate these height map tiles based on that data. And once we have the height map tiles, we're going to create these peak and valley masks, okay? So like quote-unquote sketches. So we can then get these kind of image pairs between, like the sketches we generated and pair that with the actual, terrain so that machine learning can learn a mapping between these things. So unlike the first example, where we kind of made up what the terrain was going to look like, right? We totally generated that from scratch. That was an example of data synthesis. In this case, we're kind of getting our hands on existing data. So this here is an example of data augmentation, just modifying that data bit and preparing it so we can hand that off to machine learning. Okay. So once again, let's take a closer look at how this is actually done. Okay, so step one, the downloading of the terrain data. So the way the USGS website works is that you enter in these coordinates of what you actually want, the chunk of terrain you want, and it would give you back this text file containing the zip files you're supposed to download. In this case, I'm just showing you 4 here for the sake of clarity, but in reality, this text file could be like hundreds and hundreds of lines long. This is just not something you want to really do by hand. So what we're going to do is we're going to leverage the power of these stock nodes that we have in PDG, in Pilot PDG. You can see, like the third node down, we have a text to CSV node. That's basically, ingesting that text file. And what we're doing is basically, creating a work item for every line in that text file. And then that gives us a URL, and which we can hand off to another node, like near the bottom there, like sort of third one from the bottom. It says download files. It takes a URL and it downloads that zip file. And then further down, you can see the last node there is like running a file decompress to basically unzip the zip file so we can get at the actual data inside. So here you can see kind of like how we can really leverage the stock nodes to really amplify your productivity, right? Because without them, you just end up like learning about the WinZip API and parsing all the text yourself, which just ends up being a large glob of code. And not everybody is even comfortable doing that, right? So at some point, you just might get forced into asking your programming team, hey, can you write me something like this that does this? But with these stock nodes, everything just kind of works, right? And it kind of democratizes the pipeline, so the more people can do stuff that it couldn't do before. Okay, and one last thing is also, whereas you might have noticed with Scott's earlier demos, those nodes were often pointing to other networks. Here, what you see is what you get. It's really, really simple. It's just literally do this, followed by this, followed by this. Okay, so that's the download the terrain data. So once we have the terrain data, we bring it into Houdini. Now we didn't have to use Houdini. We could have used anything that could handle the terrain data. We just happen to use Houdini because we have a really nice set of terrain tools inside. Okay. Now we can't just use that by itself because each one of these terrain tiles is huge. On the longer side is about 100 kilometers. So that's just way too huge to present to machine learning by itself. So what we're going to do is we're going to kind of chop it up into little bits, into more bite-sized chunks, so we can kind of use each one of those as a sample. And then for each one of these little tiles here, we're going to run a little HDA to mark the peaks and valleys of these things. So the peaks we would mark in red, and the valleys would mark in blue. And just like before, we're going to flatten that to form these image pairs. On the left is like this quote-unquote sketch that we've generated, and on the right is the sort of original height map that we've downloaded. And this gives us, of course, tons and tons of these pairs that we now have our data, and we're going to run through a machine learning algorithm again, and it produces this result. So this is basically, once the system's learned this, you can just basically freehand and just draw this stuff. And you can say like, hey, I want a terrain that, rocky-like terrain that looks something like this. And this is incredibly powerful because, the problem with any kind of DCC is just that they have so many knobs and levers and you just don't know what to do. But practically anybody can produce a sketch like this maybe even me. Okay, so, you just sketch and it just produces rocky mountain-like terrain, right? And of course, you don't have to sketch it from scratch if you don't want to. You can just simply hand it an image and it will do something sensible. So of course, we are SideFX, so we had to do Squab Island. All right, so to summarize this section for you, we learned 3 things here. So number 1, how PDG is really powerful and it can be used to do data synthesis for machine learning. Secondly, how it can do also data augmentation for machine learning. And lastly, how we can use the compute power that PDG is providing to do just try a lot of configurations all at the same time, run it all at the same time, or hyperparameter space searching and get all that automation, the report generation, all of that stuff. Okay. So by this time, I hope you kind of get in a sense of the breadth of this technology. We started with effects. You've seen Scott show you that, but it didn't really stop there. I showed you the applications in games and environment generation, but it didn't really stop there. And then I showed you how this can apply to machine learning, as you might guess, it's probably not going to stop there as well. So this is an extremely broad and general technology, and that is why we are launching Pilot PDG as its own product. Okay? So with that in mind, one last bit to kind of summarize and tie up the power of these stock nodes that you've seen. Throughout this presentation, you've seen that we've been using them to montage images, manipulate videos. We've downloaded stuff from the internet, unzip, zip things. But there's a whole bunch of stuff that we didn't even get a chance to talk about. We have this whole set of nodes that help you calculate dependencies, the partitioners, as Scott has talked about, but also other sets, things like mappers, that just allow you to calculate dependencies in all kinds of different ways, either through indices or spatially, you name it. Nodes to help you manipulate data, SQL, CSV, JSON, XML, all those nodes are there. Schedulers, an important point. PDG is not itself a scheduler, okay? But it works with practically like all the schedulers out in the market. Our own HQ, Tractor Deadline comes working out of the box. But if your scheduler is not on that list, don't worry. It's just a couple hundred lines of Python code, very easy to bind it to it. Source control through Shotgun and Perforce. So all that stuff is there. And it's really easy to add your own custom nodes, as Scott has mentioned. And we really want to create an ecosystem around this so that we don't just end up reinventing the wheel over and over again, so that the community can really just help each other out. Okay. Unfortunately, we didn't quite have enough time to put all that stuff together in time for the launch, but it's coming. Just in the not too distant future, look for an announcement from us. Okay, and with that, I'm pretty much done, and gonna hand it back to Cristin.
Thank you, Ken. That was fantastic. What do you think of those ML demos? Looking good? Yeah, they show a lot of promise. It's really just the early days, and ML will be in our sights for, I think, for years to come, both in terms of establishing the framework, quite possibly based on PDG. We have yet to decide fully on that. And also in terms of solving domain-specific problems, like what you've seen here, terrain generation, deep posing, up-resing flip fluids, and whatnot. All right. I think we're coming close to the end of our PDG presentation tonight. We've covered a lot of ground, and there's a lot that you have to take in, we understand. But we hope we've made a good case for how you can use it, the very many ways in which you can use it. And we've given you a sense of the size of this technology. It's really gigantic. And it's also big in terms of its transformative potential. And what I mean by that is that it stands to make a big difference in the way you think. And this is not the first time we've done it. If you think back in time, the first time we did something like this, we caused a shift in the way people think as they approach their CG content creation jobs. It was back in the 80s when we introduced proceduralism, and that basically defined the new mindset. And then we did it again in the early 2000s by adding Houdini digital assets to the mix. And that introduced a new currency, if you will, in the VFX, in the procedural pipeline, and also a new abstraction. And now finally, with task graphs, we're looking at the big picture. This is the next shift. Before, you had full control over the inner workings of your procedural systems. Now you have control over its overarching shell as well. So you have control over everything. Now, these are still the early days in some ways for PDG, and we expect it to grow. And who knows, maybe one day it will get to fight off space invaders. Okay, this is just to go a little light after all this theory and practice that we've introduced tonight. This is what our PDG developers did for fun. It's an actual top node, zoomed in a lot. It's actually cooking a PDG network. This is not scripted, all right? And it's all driven by the keyboard. So the little shooter at the bottom is driven by the keyboard. So this is another example of PDG. Of course, we don't mean it that way. We just wanted to show it to you for fun. All right, just before we leave PDG territory for the day, it is my great pleasure to introduce a very special guest. Bill Polson, Global Head of Pipeline and Workflow at MPC Film, is with us tonight. Bill has dedicated most of his career to designing and implementing successful pipelines for VFX and film. He has written about pipelines. He has proposed a model for pipeline architecture based on design patterns. And has kindly accepted our invitation tonight for a short Q&A. Welcome, Bill, and thank you so much for coming.
I'm new to this. I'm new to this job, so I just want to say there's a tremendous amount of amazing work being done at MPC. I'm responsible for none of it at this point. My main goal is to not screw it up.
Well, it's a very opportune moment to have you here. We're about to release PDG. It's something to do with pipelines. You know, you spent 19 years at Pixar overseeing several generations of pipeline. Again, you've written about pipelines, and now at MPC, you've taken a really thorough look at PDG. How do you think PDG can contribute to the pipeline at MPC?
Well, it was, I actually wrote out answers to this question, and the opening of this presentation hit all my points exactly. The first thing is it's going to be a much better Houdini, and we're already incorporating it into workflows and effects and environments and so forth. That work is well begun. A big vision for us is to assetize our workflows and start building these graphs that the VFX soups and the CG soups can snap together. It's exactly what was shown here. This is what we want to do, and we think PDG is the right kind of way of thinking about it. We've been experimenting with this, and it's very promising. This is our vision to do exactly what was demonstrated.
Thank you, Bill. One more question,
sure,
if I may. The second question is about USD. That's something you know a lot about. You saw it in its infancy at Pixar. You saw it grow out of its shell. You were one of the first people to promote it externally, I remember. And now we're seeing USD being adopted more and more by studios, and many other studios talking about adopting it. Do you see any synergies between USD and PDG?
I do. Just at one level, you can think of USD as describing data, and PDG is describing processing. So that's kind of obvious. And I think there are a lot of systems that decompose in that way. But what is so compelling about PDG is that the dependencies are, if you really watched carefully, you saw that the dependencies are kind of independent of the shape of the data. They're very reactive to the data. And so we see this as a way of decoupling these problems. The processing dependencies are not tied to the actual data description. This lets the two evolve independently and splits the problem space up very nicely. So that is why I think this is so compelling. I think PDG and USD will go together very well.
Thank you, Bill. We look forward to working with you and talking some more in the future. Thank you.
Thank you.
All right, welcome back, Scott. And now to something completely familiar. Let's go to the second part of our presentation today. This is where we want to cover some of the main features that are non-PDG related in Houdini 17.5. It's not something we set out to do. Like I said at the beginning, we wanted to put our heads down and just get PDG out the door best we can. But we've been developing some features for Houdini 18 that happen to be ready now. So rather than holding them back from you for still a couple of months, we thought of including them in this release. So here is Scott again to give us a quick tour of those. Scott.
All right, thank you, Cristin. Okay, let's just dive right in. So in Houdini 17, we introduced a new whitewater solver for giving better whitewater effects, more fidelity, more control. But of course, when you're generating whitewater, you tend to generate enormous numbers of particles, especially depending on what's happening in your scene. So it really is helpful to be able to distribute these simulations. So for Houdini 17.5, we've created sort of two versions of this. A sliced distributed simulation, and this is sort of the one that you probably are imagining, where data is shared between the slices, so they keep in sync with each other, which is great. You can go very large, but there is some overhead to that because data is pushed between the slices. And then what we're calling a clustered distribution, where essentially the slices actually don't talk to each other at all, and they can be run completely independently in parallel. Of course, the downside of the clustered simulation is that there is no communication, so it's possible that you're going to get slightly different results on either side of the slice. However, practically in our experiments, and as you can see here, it turns out to not always be the case, especially in situations like this where the underlying sim is very stable across the slice anyway. And here, just to sort of drive that home, is a render of the clustered simulation to see that there's no real discontinuities here. This is sort of a best case scenario because the ocean is sort of known on both sides very well. But still, really nice to be able to get these kinds of results. So back in Houdini 16.5, we introduced narrowband fluid simulations. And essentially, if you're not aware, that means that we simulate the particles only at the very surface of the fluid, but in the deeper areas, we basically only deal with the volumetrics data. So there's a huge gain, a little bit in performance, but a lot of gain in memory because you're actually simulating fewer particles. And in 16.5, this was mostly contained to tanks, deep things. And then in Houdini 17, we made some improvements to it, and we were able to handle things like rivers, and basically any kind of fluid simulation can get some gain from this narrowband approach. But of course, as soon as you say, hey, we've saved you, all these gigs of data, isn't that great? You immediately say, okay, well, now I'm going to use all my memory anyway, right? So you just scale up the number of particles to these huge numbers, in which case you still want to be able to distribute this. So maybe you're rendering 1 billion particles, 5 billion particles. And so in 17.5, we've also allowed you the ability to distribute these narrowband simulations as well. So you can scale up as large as your render farm, essentially. So it's not just about making the underlying technology for doing simulations better, but we want you to be able to visualize it better as well. So this is a viewport flipbook of the new GPU-based smoke shader, which basically is designed to give you as high fidelity as possible in the viewport, so that you can actually really set up lights and understand what your sim looks like without having to pay a huge cost. And you can see that it's not just faster, but it's also much higher fidelity. You can see this self-shadowing within the smoke itself, just generally a higher throughput. And the interesting thing is that it's also faster, so you can interact with it. Very high resolution volumes in Houdini in the past were actually kind of painful to work with. You have to pay a really big cost to move a light. However, now in real time, you can take this very high resolution simulation here and just interactively drag these lights around. You can use spotlights, which we could not do previously in the past, so you can use the lights that you're used to working with as a lighter. And so you can get really nice results. You can see how the shadows cross across the surface of the volumes. And again, we're talking about a very high resolution volume here. So when we pull this final light out and you see all the detail that's in there, you want to be able to see that in the viewport. If you're going to spend the time lighting this, you don't always want to have to go to the render. You want to get as close as possible in the viewport before you pay that extra cost. And that's not just for volumetrics. We've also made some big changes to the Houdini viewport to try and get parity with render. So the principled shader now has a much better representation of what the final result will look like in the viewport compared to something like Mantra. So again, on the left, the viewport, on the right is Mantra. Now Mantra has, fancier technology behind there. It's doing very detailed shadows. It's doing all sorts of reflections and so on. But still, you get a very, very close representation of what you're going to get by looking at the viewport representation. In fact, you can kind of put them side by side. In a lot of cases, it's sort of indiscernible which one is which again means that as you're working with these assets, you don't have to worry as much about, like, well, am I really seeing what I think I'm seeing? Like, do I have to send this to a render or not? But it's not just about matching Mantra. In fact, a lot of this work was done to make sure that we also match other software in the industry, because a lot of times the reality is you're pulling data in from somewhere else or you're pushing it out into another piece of software. And if you're doing that, you want to make sure that they match as close as possible, that you can feel confident that what I'm working on in Houdini will match whatever my end product is going to be, whether it's Unreal or Substance and so on. There's also a new game dev shader that has some other features to make sure you can match things like Michelson tangent space, normals, and so on. But this is the default principled shader that you're looking at here. Again, since this is a 17.5, so it's sort of in the middle of a schedule, we also built some foundational tools. The measure SOP is not the most exciting SOP in the world, but it's very fundamental to a lot of workflows. So it's been rewritten from the ground up. And not only has it been rewritten sort of internally to do the calculations in a better way, to make it faster, we've also added a lot of visualization features that were not possible before. So in the upper left, you can see a histogram embedded into the viewport to help you understand what you're looking at, the data you're looking at, as well as these little arrows that you see are all handled using visualizers. So this is a much faster, more efficient way of representing this data. And then, of course, that data can be baked down into attributes. So it's not just for visualization, it's just a way to improve when you're trying to find those values, trying to find exactly the pieces that you're looking for. And like I said, it's been basically rewritten from scratch. So we also have a lot of new ways of doing the measuring. You can see here again how important having this live visualization in the viewport is, and how it's nice and fast so that you can narrow down to exactly the information you're looking for and then apply that to other effects further in the pipeline. Again, MeasureSop, a foundational tool, but very important for work to come in Houdini 18. And of course, we wanted to let you get your hands on it sooner. Another one of these tools that just helps you expand an existing tool set is a terrain alpha cutout. And essentially what this means is that we can apply what is essentially an alpha mask to a terrain, so that when you generate the geometry, you get something like this, or you can render it this way. And this is just a way of extending the functionality of height fields, which by their nature were sort of square. with hard edges on the ends. So this allows you to sort of cut out a chunk of terrain, even if you just want to do sort of an effect like this, an interesting sort of floating island kind of effect, or if you were doing something maybe that's going to be processed later. So maybe you want tiles, hexagonal tiles for a game or something like that. This would allow you to create those shapes that were difficult to do previously in Houdini. We've also changed the way you interact with some things in the viewport. So we can now create patterns of selection. So you select the initial pattern, and then you can expand that pattern in the selection. So these are tools that were available in things like the group SOP, for instance. But they really lived outside of the viewport. You had to change parameters on the group node. This is an interactive tool. So if you really just like, well, I just need to select these things, and I want a fast way of doing it, and it doesn't have to be a procedural effect, this is a super fast way of doing it, and it also really nicely expands in other directions. So you can follow a path or expand perpendicular to that path and get reasonable, obvious results. And continuing down that line, we also have a selection by face normal. So in this first example, we have a 60-degree spread angle. So even though this is sort of a connected piece of geometry, I can very quickly make selections because it's only going to select the connected pieces of geometry that match the normal that you clicked on. So I can very quickly select parts of this model without having to go in and individually select them. And when you're working in a modeling case like this, it can be really useful to do that. You can really rapidly isolate parts of your model. And now we've changed the angle to 90 degrees, and you can see now we'll wrap around the corners of objects, but we won't go too far. It'll stop at that 90-degree limit. So again, it allows you to really rapidly make selections on geometry for work down the road. This is especially great when you just ingest the model and maybe you just need to isolate something really quickly in the viewport. But it's not all about like selecting things. We want more interactivity with our base tool. So here's just a neat-looking rigid body simulation using a lot of the constraints that we developed previously in Houdini. They've been around for a while, but constraints are generally something that are generated procedurally. You know, there's a system of tools for saying like, well, let's connect these points together if they're close together and so on. And that's really useful, especially when you want to do something large scale where you don't want to definitely hand place these. But sometimes you do. You want a specific thing in a specific area. So in this case, we're going to take a look at a viewport state that uses the Python states that were introduced in Houdini 17 to make an interactive tool for building constraints. So you can see I can just draw on the viewport, and it will connect those two pieces of geometry together just with a stroke. And this is using the new constraint from line tool. So I can preview the result. In this case, they're pins. But it's not just placing them. I can edit them. I can draw them quickly. You can see, visualize which pieces are being connected, and then edit ones that already exist. So again, it's taking some of that interactivity that you want and taking it away from a pure SOPs workflow and putting it into the viewport so that you can very quickly create these constraints in a very artist-friendly way, but still have the backing of the procedural network, right? The result is still the procedural network you would expect. There's also a new tool where you're building constraints by curves. And so in this case, we want to connect these pieces together across this gap. So we can just draw in the viewport, and it'll start connecting them automatically. And if we increase the radius, you can see these stitch lines sort of jumping across the gap. So you can very quickly just paint in where you want things to be connected together and immediately get results. So again, not taking away the procedural tool, but augmenting the procedural tool with this artist-driven approach. So once we have the constraints set up, we can preview the results just on these pieces in isolation, and then make some changes, maybe make it stiffer, and then see the results again. So it's really, again, about allowing you to more interactively do work that you could already do in Houdini, but in a less hands-on way. And since you've seen lots of these montages throughout this event, we wanted to show you a couple more with some extra pieces of information here where we're showing different types of information all at once. So this was, of course, generated via PDG, and we're wedging out these variations of these explosions. But you can see that we can also embed other information in here. So we're showing, you know, the final geometry, the constraint network, as well as all of the stats, all of the values that have been manipulated to get these results. So if you're trying to find a good value, it's not sort of just a random search. You can actually see like, oh, the ones in the middle here are actually doing pretty good. Let's continue on in that vein, maybe more so than the one on the far upper left. So again, just a callback to PDG here and see how useful it is even in a case like this. And then just because it looks cool, I'm just going to show this again because it looks cool. So vellum. So we introduced vellum in Houdini 17, and we're going to show you an example here of per point friction, something that did not exist before. And so you can see that these sort of weird guys, where they've been painted with this sticky substance, they slide more or less. So you could vary friction before, but it was on a per object basis. And now different parts of the material can react in different ways. So truly per point friction on both the collider and the vellum object itself. But it's not just cloth, it's also the whole vellum solver. So here's a vellum grain simulation where we've sort of increased the friction here on the glass, and so the particles tend to stick to that area. So again, just increasing your options for these types of simulations, giving you more ways to interact with it. And continuing on that vein, we've also added new constraint types to the vellum solver. So if you're not familiar with what a constraint type is in vellum, it essentially is a way of defining the physical properties of something. So in this case, we're creating these fiber constraints. And those are basically implied fibers inside the three-dimensional space of this object. And then they can be flexed along the fiber direction. So in this case, we're flexing them along an axis, essentially. But it's not just along an axis. Of course, you can define these fiber directions using attributes, using vex. And here we're sort of pulling to the center of the object altogether. So you can see it's sort of stressing and pulling together. And there's also some volumetric constraints here helping preserve the volume when this happens. Now, these are just provided as interesting tools to use, but you can imagine in the future that some of this technology could be applied to things like skin and muscles for muscle simulations. So taking some of that vellum power and applying it to other cases. So here's an example now on an actual character, this frog. And we're going to actually generate these fiber directions interactively here. And this is actually just taking advantage of essentially our fur grooming tools to set the fiber direction on this creature. So you can easily set them like this. Obviously, this can be driven, as I said, by a expression or other type of procedural effects, but sometimes it's useful to be able to do this by hand. Now, when we play this simulation, you're going to see this really interesting result where our frog, he sort of undulates in a very suggestive sort of way. So this is just using the fiber constraints that we just set up. But of course, once we saw this and saw how interesting these frog characters are, we thought, well, let's put the per point friction and this new way of animating together to create an interesting sort of effect. And so basically, we increased the friction on their feet and let them sort of flail around to see who would win this race. My money was on the one in the middle, but it actually turns out the guy in the bottom wins the race. All of the other frogs that lost were actually eviscerated, so we didn't need those. We only want the winning frogs in this case. So to go along with this, a while back we started using these nodes in Houdini that had this sort of 3 input, 3 output method. And the problem with that is that you could only ever view one output. You would only see basically the first output. So something that we've added purely as a UI feature is the ability to analyze each of the outputs individually using the middle mouse button information. So you can actually choose which output you're looking at. And this is really useful because previously you would have to put down a null, connect it to the output, and examine the geometry there. So now not only can you use the middle mouse button information, but you can also tell the node itself to show me the data from each input, not just look at it in the middle mouse button, but update the viewport. And of course, as you would expect, this is also extended to the geometry spreadsheet. So you can just select which output you're viewing and get the results there. So this is really just a huge improvement to your workflow with these sort of chained nodes where you really want to be sure what data is being passed along which wire. So this is just a way of really elevating the overall workflow for these new types of nodes. And so that is finally the end of this presentation. We've spilled all the frogs. They're all on the table. And so just to wrap up here, I'm going to once again bring Cristin back on stage just to wrap up. So I hope you enjoyed the show, and thank you very much.
Thank you, Scott. That's fantastic. I think one thing we need in that frog race is some machine learning, eh, Ken? This concludes our presentation of Houdini 17.5. We hope you've enjoyed it. We hope we've given you a lot to think about. Clearly, the big entrant here in the Houdini ecosystem is PDG. But the list, if you don't mind playing it, Scott, is actually not that small. And we hope that you'll find a couple of good gems in there that you can use right away. Some of the features you've seen speak directly to some bigger projects that are underway. The fiber constraints is all about getting to muscle and skin simulation. We're looking both at classic FEM and vellum now and see how they might coexist or something along those lines. And then the other really big one is the lighting and the quality and the performance in the viewport. And that is all about a project that I hinted at when we launched Houdini 17, Project Solaris, which is about lighting, rendering, USD, everything put together, and that's coming in Houdini 18. Also, if I may invite you to take a look at some of the great new tools that our game dev team have put together. There's some really amazing stuff in there. Even the texture baker, I believe, is way, way faster in 17.5, and then there's support for Alice Vision, which is photogrammetry support in the game dev suite. So lots to look for and play with. We hope you enjoy Houdini 17.5, and we look forward to seeing you again soon for Houdini 18. Thank you. And just before we go, I'd love to give a big shout out to all the people who have made Houdini 17.5 possible. Well, first, Houdini 17.5 is coming in just a couple of days by mid-March. And then the team. First, our amazing team of developers. Goodness gracious. PDG developers, and everybody else. Our technical directors, a growing team of people with really production-savvy skills. Our QA and documentation department, all three of them. And then, of course, our Waterloo Co-op students. And in the end, big thank you to all of you, our alpha, beta testers, and all of you who use Houdini and really give us good reasons, amazing reasons, to continue to try to better ourselves in our product. So thank you again, everyone.